velocity and acceleration questions. Second part of this review. So the first question is pretty easy. It says, what would be the acceleration of a turtle that's moving with a constant velocity of 0.25 meters per second to the right? If something's moving with a constant velocity, that is, its velocity is not changing, its acceleration is going to be 0. Remember, acceleration is change in velocity over time. Your change in velocity is going to be 0. And 0 divided by anything is 0. All right, so answer to this one is 0. Makes it easy. All right, next one. Sketch velocity time graphs for the following motions. Okay. It's important to remember that these are velocity time graphs now, not position versus time graphs. So here's a velocity time graph. Start with A. For a city bus moving with a constant velocity. Your time is always on the x-axis, the velocity is on the y-axis, and it would just be a flat line. It says constant velocity. Here's a velocity time graph for velocity. A wheelbarrow that's speeding up at a uniform rate of acceleration while moving in the positive direction. So you know it's positive, so it's going to be up here. It's going to be in this quadrant, right? And you know it's going to look like that. The reason it's a flat line is because it has a uniform rate of acceleration, all right? And it's speeding up, so it's getting faster and faster and faster as time goes by, and it's moving in the positive direction. All right, C. A tiger that's speeding up at a uniform rate of acceleration while moving in the negative direction. Okay, there's velocity, there's time. The reason I also drew this negative section is because you know it's going more and more negative as time goes by. So it looked like that. I need to leave the arrowhead off. That's what your line would look like. All right? Starts at 0, gets more and more negative as time goes by. Further and further down. D. An iguana that's slowing down at a uniform rate of acceleration while moving in the positive direction. So, time, velocity. Okay, the iguana starts positive, and it's slowing down. So this whole time, it's got a positive velocity. It's just getting less and less and less and less and less. And then last but not least, E. A camel that's slowing down at a uniform rate of acceleration while moving in the negative direction. Time, there's velocity, okay? Camel's moving in the negative direction, so you know its velocity is going to be negative, but it's slowing down, so it's negative, and it's going to get less and less and less and less and less until the camel comes to a stop. All right? There you go. There's 17. 18. There's 18. Okay, it's got strobe photographs, and it tells us one of these has the acceleration that's positive, one acceleration is negative, one the velocity is constant. If it's constant velocity, it's going to cover the same amount of distance every time. So this one right here, see how this distance is always the same? Okay? This one right here is constant velocity, that'd be C. If it's accelerating, that distance is going to get greater and greater as time goes by. So it starts small, a little bit bigger, a little bit bigger, a little bit bigger. This one right here is the positive acceleration, so that'd be A. Which leaves us, through process of elimination, with this one, the acceleration is negative. If you look at this one, it's actually a little more complex than what they just say. The acceleration starts out positive and then becomes negative. All right? So, it's just the way it is. All right, what do we got next? Actually, I'm thinking about that. If you, no, this could be, yeah, we'll leave it at that. All right, 19. If a car is traveling eastward, can its acceleration be westward? So let me see if I can do this from your perspective. Car is traveling eastward, can its acceleration be westward? And the answer is yes. That would just mean that the car is slowing down. You can have an acceleration, you can have a velocity in one direction, say this is your velocity, and an acceleration in the other direction if you wanted to. Let's say my velocity was 10 meters per second going eastward, and my acceleration was 1 meter per second squared going westward. That means every second this is going to go down by 1. So this thing would be going 10 meters per second, then 9, then 8, then 7, 6, 5, 4, 3, 2, 1, 0, so it stops. Then if we kept on with the acceleration, it would actually stop and start moving in the other direction. It would look like something going really fast this way and slowing down, and then eventually coming back that way. All right? All right. What's next? We're up to problems now, right? Okay. So when you have uniform acceleration, you can use the kinematic equations. There are 4 of them. You've got 1/2 initial plus final times time. You've got initial times time plus 1/2 acceleration times time squared. You've got final velocities, initial velocity squared 2a delta x. Final equals initial plus acceleration times time. I don't expect you to have those memorized. I will give them to you on tests or quizzes anytime you need them. Let's see. That being said, I wouldn't be surprised if by the end of this course you had some of them memorized just from using them so much. Car is traveling a straight line. It has a velocity of 5 meters per second. I'm doing number 20. First thing I do is I write down the givens. Its initial velocity is 5 meters per second. It has an acceleration of 0.75 meters per second squared. 0.75 meters per second squared. Car's velocity, after an acceleration of 0.75 meters per second squared, the car's velocity is 8 meters per second. So afterwards, its final velocity is 8 meters per second. In which time interval did the acceleration occur?
Mr. Griffin, please call extension.
How much time did that take? What equation can I use? I can use this one. How do I know I use this equation? This is the only one that has those 4 things in it. All right? If you don't believe me, try plugging it into another equation. You will find you don't have the right variables. So I rewrite the equation. 8 equals 5 plus 0.75 times t. And grab a calculator. All right. Can't combine these 2 things because this one's got a t attached to it. So you subtract 5 from each side. 3 equals 0.75 times t. 3 divided by 0.75 gives you 4. 4 seconds because it's a unit of time. It takes 4 seconds for this acceleration to happen. All right? Number 20. 21. Car is traveling at 7 meters per second. So initial velocity is 7 meters per second. Accelerates at a rate of 8 meters per second squared. 0.8 meters per second squared. For 2 seconds. For 2 seconds. Find VF. Ooh, they're nice enough to even tell you what variable they want. Find final velocity. Once again, the only thing that's got those 4 things in it is this guy. VF equals VI plus A times T. Notice I rewrite the equation each time. If you don't rewrite it on your test or quiz, you will not get credit. So make sure you show me givens, formula, and when you finish it, final answer in units. 7 plus 0.8 times 2, 8.6 meters per second. There you go. Gibbons formula, final answer, units. 4 points, you got it. 22. A snowmobile has an initial velocity of 3 meters per second. If it accelerates at the rate of 0.5 meters per second squared for 7 seconds, what's its final velocity? Plugging everything in. df equals vi plus a times t. df equals 3 plus 0.5 times 7. df equals 6.5 meters per second. All right, so that's the answer for A. All this work here is for A. Now they changed the acceleration for B. So for B, we've got the same givens. Still got VI of 3 meters per second. What else does it have? It's still got a unknown VF. Yeah, still got an unknown VF. And you know that its acceleration now is negative 0.6 meters per second squared. You want to know how long it'll take to reach a stop? Oh, there you go. If you want to know how long it'll take to reach a stop, that tells you that the VF is going to be 0. And they're asking you how long, so they want to find time. So time's the guy they want to find. Use this equation. VF equals VI plus A times T. Plug in. 0 equals 3 plus negative 0.6 times T. Subtract 3 from each side. Divide each side by negative 0.6. And I get time 1.8 seconds. So that's big. It'll take a 1.8 seconds, that thing, to slow down and stop. All right, that's the snowmobile problem. Now we got a car problem, number 23. Car moving westward along a straight level road increases its velocity uniformly from 16 meters per second to 32 meters per second in 10 seconds. It starts at 16. It ends at 32. It takes 10 seconds. Question is, what's the car's acceleration? And that's for A. So let's solve that. We can use this equation again. Df equals Vi plus A times T. 32 equals 16 plus A times 10. Solving that. 32 minus 16 divided by 10. Its acceleration is 1.6 meters per second squared. 1.6 meters per second squared. Second part of the problem asks, what's its average velocity? Couple ways you could do this. I could find the total distance that it covers, and I divide that by the total time. Or I could take my two velocities. I could take my initial velocity and my final velocity, add them together, and divide by 2, because there's 2 of them. 32 plus 16 divided by 2 gives me 24 meters per second. Fun thing about this, you notice that this right here, this equation, is initial velocity plus final velocity divided in half. So that's the average velocity times time. So this kinematic equation actually comes from the fact that your average velocity times time will tell you how far you went. Just a neat thing to say. All right, 24. Oh, wait, it's got one more question. It says for part C, how far did it move while accelerating? So they want to know what its delta x is for all these givens that you already found. I've got a lot of stuff. I could use any of them. I'm going to use this first one. Delta x equals 1/2 of initial velocity plus final velocity times time. I just got done telling you that this section is going to equal 24. So 24 times 1.6 is my answer. 24 times 1.6. It went 38.4 meters. There we go. All right, now on to 24. A ball initially at rest rolls down a hill with an acceleration of 3.3 meters per second squared. So the ball is initially at rest. I equals 0. The acceleration is 3.3 meters per second squared. Accelerates for 7 seconds. How far will it move? So you're looking for delta x. Here's something interesting. If something's going down, we say it's negative. If something's going up, we say it's positive. In another convention I'll try to keep to, if something's going to the right, it's positive, and if it's going to the left, it's negative. That's another convention I'll try, or that I'll try to hold to. Doesn't really matter here, but it's worth pointing out. So what am I trying to find? I'm trying to find my delta x. I could use, don't have a final velocity, I got an acceleration, an initial velocity. I could use this one, this guy right here, and that would do it. All right, delta x equals initial velocity times time plus 1/2 acceleration times time squared. So your delta x is 0 times 7.5 plus half of 3.3 times 7.5 squared. 0 times 7.5 is going to be 0. When you're doing this, make sure you square this first. Order operations. So you do 7.5 squared times 3.3 times 1/2. Doesn't matter what order you multiply them in. You could do the 1/2 times the 3.3 first and then multiply it. But it matters that you square this first. So my delta x is 93 meters per second. There you go. All right, 25. A bus slows down uniformly from 75 kilometers per hour, which is 21 meters per second. So its initial velocity is 21 meters per second. Why did I choose to write down the 21 meters per second instead of the 75 kilometers per hour? I noticed this other stuff is in seconds. All right, and I want to keep my units consistent. So rather than have to convert those seconds to hours, I'm going to do it in meters per second. My time is 21 seconds. And it slows down to 0. 0 kilometers per hour is the same as 0 meters per second. And that would be your final velocity. And the question is, how far does it go? What's its delta x? And to solve it, we can use the first equation. Delta x is 1/2 initial plus final times time Plug everything in there. Delta x equals half 21 plus 0 times 21. I both 21? Look at that. Alright, so you would have 21 plus 0 is 21. 21 times 21 is some number I don't know. 21. 441 times a half. And you get 220.5 meters. That's 25. Once again, given formula, final answer, units. 26. Car accelerates from rest at -3 meters per second squared. Accelerates from rest, so you know its initial velocity is 0 meters per second. What's the velocity at the end of 5 seconds? What is the velocity? That's what we've got to solve for A. So looking at that, I could use this equation. Final equals initial plus acceleration times time. Final equals 0 plus -3 times 5. -15 meters per second. -15 meters per second is the answer to A. What's the displacement after 5 seconds? What's my delta x going to be? I could use 1/2 initial plus final times time. If I plug into that, I get half of 0 plus, 0 plus a -15, which is the same thing as 0 minus 15. Times time. My time is 5 seconds. Zero minus 15 times 5 times 0.5. Looks like that sucker went -37.5 meters. Good question. Negative displacement. What does that mean? Well, it means that it went backwards. So it went backwards 37.5 meters. All right. 27. Car accelerates uniformly from rest, so the car's initial velocity is 0. Uniformly means the acceleration doesn't change, stays the same, which is good. If the acceleration changes, our equations don't work anymore. To a speed of 65 kilometers per hour. So it's final velocity. I'm not going to do it in kilometers per hour. I'm going to do it in meters per second. Give it to me here. 18 meters per second. That's its final velocity. In 12 seconds. Find the distance the car traveled. What's your delta x? You could use, which one has a VI, a VF, a T, and a delta x in it? Nope. 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 This one. Process of elimination. I went through all of them. All right, so delta x is 1/2 0 plus 18 times 12. You do some mathemagic with the calculator. 18 times 12 times 0.5. 108. 108 meters. Givens, formula, final answer, units. Probably going to say that a lot in this video. So that's 27. 28. Let's scroll up. Car starts from rest. So VI equals 0. Travels for 5 seconds. T is 5. With a uniform acceleration of 1.5 meters per second squared. A is 1.5 meters per second squared. Driver applies the brakes, causing a uniform acceleration of, whoa, what's going on here? 2 parts to this problem. This part, where it has this acceleration. And then the second part, where the driver applies the brakes, causing a different acceleration. So I'm going to break it up as such. So here's part 1. Part 1. And let me put part 2 down here. For part 2, he applies the brakes, he or she applies the brakes for 3 seconds. The acceleration is negative 2.1 meters per second squared. And you want to know how fast the car is going at the end of the braking period. So you want to know the final velocity here. Okay? So this is part 2. So part 1, car starts at rest, 5 seconds, it accelerates at this. Alright? I want to find out for part 1 what the final velocity is. So by the time you get to the end of part 1, how fast is that car going? And that's an easy enough problem. I can use this equation right here. I can solve it. VI plus acceleration times time. Plug stuff in. 0 plus 1.5 times 5. 1.5 times 5. That's what, 7.5? Yep, 7.5. So, after the car has gone through this period of acceleration, this part 1, it's going 7.5 meters per second. And then the driver hits the brakes down here. And here's something cool. You can take the final velocity from this first part, and you know that's how fast the car is going to be going when it enters this part. So the initial velocity for part 2 is going to be 7.5 meters per second. That's where he left off with in part 1. Now the driver hits the brakes. We want to know how fast he's going after a certain amount of time. We can still use this equation, VF equals VI plus A times T. We can plug into it. VF equals 7.5 minus 2.1 times 3. And you will get a final velocity of 7.5 minus 2.1 times 3. 1.2 meters per second. So the answer to this first question is, at the end of the braking period, the car is gone 1.2 meters per second, or is going 1.2 meters per second. The next thing it asks is, how fast is the car going at the end of the braking period? We answered that. And how far has it gone from its start? There's the first answer. How far has it gone from its start? So we're going to need to figure out delta x here. We're going to figure out how far it went during the accelerating period. Then we're going to need to figure out delta x here. Then we're going to need to take the two of them and add them together, and that's how far it went during the whole time. It's got some time where it's speeding up, and it's got some time where it's braking. So in order to get delta x, there's actually quite a few things I could use. I think the easiest is probably this equation. So let me plug in. I'm going to erase this. I'm going to add in this given that I got from the last part, 1.2 meters per second. I'm going to erase this, so I got some more room to work with. Now I'm solving for part 1 what delta x is. 1/2 initial plus final times time. So my delta x is 0 plus 7.5 times 5. Bingo bango. My delta x is something. 7.5 times 5. 18.75 meters. All right. So for this part, it went 18.75 meters. How about this part? Well, I'm going to use that same equation. Delta x is 1/2 initial plus final times time. Delta x is half of the initial 7.5, the final is 1.2, and the times 3. Delta x is 0.5 times, in parentheses, 7.5 plus 1.2, in parentheses, times 3, 13.05 meters. I can write that here, 13.05 meters. And then, to get your final answer, 18.75 plus 13.05, 18.75, 31.8 meters. That's how far it went over the whole trip. Okay, so that's 28. Let's try 29. Ooh, I erased some of my kinematic equation there. Let's see, df equals vi plus acceleration times time. 29. A boy sledding down a hill accelerates at 1.4 meters per second squared. He started from rest, so his VI is 0. In what distance will he reach a speed of 7 meters per second? So you want your VF to be 7 meters per second. And you're looking for what distance that would take. What equation has delta x, a VI, a VF, and an A in it? This guy. So VF squared equals VI squared plus 2A delta x. So you plug in 7 squared equals 0 squared plus 2 times 1.4 times delta x. And you will get for your answer 7 squared minus 2.8. 46.2. 46.2 meters, because it's a delta x. There you go. Funny, they throw you a tough one in 28, and 29 is like easy. All right, let's take a look at 30. 30. 30 says, velocity time graph for an object moving along a straight path is shown in this figure. Find the average accelerations during the time interval 0 to 5. All right. 5 to 15. And 0 to 20. So they want average acceleration. All right. Acceleration is change in velocity divided by time. So from here to here, how much did your velocity change? Well, it didn't. you were at negative 7 meters per second. You stayed at negative 7 meters per second the whole time. So from 0 to 5, your average acceleration is 0. How much did it change from here to here? Well, you started at 7 and you went to 6. So 6, let's see, minus a negative 7 is going to give you, what, 13? So change by 13 in how many seconds? 10 seconds. So 13 divided by 10 would be 1.3 meters per second squared. So your average acceleration for this part's 1.3 meters per second squared. And then from 0 to 20, 0 you're at negative 7, come all the way over to 20, you're at 6. So you changed once again by 13 meters per second. So your change in velocity was 13, but this time it took you 20 seconds. So your answer would be 13 divided by 20, which is, what's that? 6.65. 0.65, maybe? Yeah, 0.65. 0.65 meters per second squared. All right, they're just checking to make sure you can read a graph, really, at that point. All right, moving on. Oh, this is a fun one. Plane lands at the velocity of 120 meters per second and accelerates at a maximum rate of negative 6 meters per second squared. So let's write that down. Your initial velocity, 120 meters per second. Your acceleration is negative 6.0 meters per second squared. From the instant the plane touches the runway, what's the minimum time needed for it to come to rest? So for A, we're saying, all right, our VF is going to be 0, right? And how much time is that going to take? Easy one, right? Use this bottom equation. VF equals VI plus acceleration times time. You plug your numbers in. You get negative 120 divided by negative 6.0. You get 20. It takes 20 seconds for this thing to stop. Okay, and then the next question is, can this plane land on a naval aircraft carrier where the runway is 0.8 kilometers long? There's a couple ways you can approach this. You could say, all right, if I set my delta x equal to this, if I set my displacement equal to this, and I calculate what my final velocity is going to be, will it be 0 or less than 0? If it is, then you succeed. Or you could take a look at this, and you could plug this in, and you could see, okay, with that acceleration, that initial velocity, that final velocity, what kind of time, or what kind of time am I going to end up with? Let's see, how could you end up doing that? Use that equation. Initial velocity times time. It'd be a little bit tougher. You could try using this equation, plug in your 20 seconds, and see what your delta x is. So you could, another way you could look at it is you could take these parameters they gave you initially in the beginning, plug them into this equation and say, okay, in that time that this thing's taking to stop, how far does it go? And then compare the answer you got to this and see if it will go too long or go too short. I think I'm going to go that route because it seems to be the easiest. So I'm going to say, I'm going to use this equation. I'm going to say, okay, I know I got 20 seconds. I want to see how far this thing goes in 20 seconds. That's the minimum amount of time it takes to land. So half of 120 plus 0 times 20. All right, 0.5 times 120 times 20. 1200 meters. All right, so it takes 1,200 meters for this thing to land. Your runway is 0.8 kilometers long. You'll remember kilo means times 1,000. So this is, if you multiply 0.8 times 1,000, you get 800 meters. Runway is 800 meters long. It needs 1,200 meters in order to be able to do it. No, it cannot land. That's your answer. All right, 32. Woohoo, only one more after this. Sailboat starts from rest, accelerates at a rate of 0.21 meters per second squared. Acceleration is 0.21 meters per second squared over a distance of 280 meters. Find the magnitude of the boat's final velocity. The final velocity. Oh, and one thing I forgot, it starts from rest. So its initial velocity is 0. All right, which equation has an A, a delta x, a VF, and an I in it? This one. VF squared equals VI squared plus 2A delta x. You plug into that equation. I get VF squared equals 0 squared plus 2 times 0.21 times 280. 2 times 0.21 times 280. 117. VF squared equals 117. To get just VF, I gotta take the square root of each side. Alright? And I get my VF equals 10.8 meters per second. 10.8 meters per second. So that's the magnitude of the boat's final velocity. And it says find the time it takes to travel this distance. Well, I got 1, 2, 3, 4 givens now. And use basically anything that has time in it. I'll use this one because it's pretty simple. VF equals VI plus A times T. Oof, handwriting is just getting worse and worse. 10.8 equals 0 plus 0.21 times T. 10.8 divided by 0.21 gives me 51.4 seconds. Takes a while. 51.4 seconds. All right, and last but certainly not least, number 33. An elevator is moving upwards at 1.2 meters per second. Its initial velocity is 1.2 meters per second. Upwards, positive. Experiences an acceleration of 0.31 meters per second downwards. Acceleration, negative 0.31 meters per second squared. Downwards, negative. Over a distance of 0.75 meters. 0.75 meters. What will its final velocity be? That 0.75 meters, by the way, is going to be going up. That's why it's positive. Okay, if it's got a positive velocity, it's going to keep moving in the positive direction. Its displacement is going to be positive. So what's its final velocity going to be? Well, we could use this guy right here. Vf squared equals Vi squared plus 2a delta x. Vf squared equals 1.2 squared plus 2 times negative 0.31 times 0.75. 1.2 squared plus 2 times negative 0.31 times 0.75 gives me 0.975. Take the square root of that, and I get 0.98 meters per second. It's a velocity. Right? All right. That's all of them.